Hello chemistry students. In this video I'm going to go over equilibrium. Alright, so before we can deal with equilibrium, we're going to talk about what reversible reactions are. So it may or may not surprise you, but a lot of reactions don't go to completion. And what we mean by reactions don't go to completion is that they don't, like if you take the product or take the reactants and put them together, they don't react entirely. In other words, they don't the reactants don't completely convert to products. So what that means is that in a reversible reaction that the products can reform into reactants, and so the reversible reactions are going to be shown with a double arrow. And that gives us this situation of dynamic equilibrium. So in dynamic equilibrium, the products, or product in this case, the product is still reacting to form reactants, and the reactants are reacting to form product. And that may sound a little bit weird, but as long as those two things happen at the same rate, there appears to be no change in the reaction as far as the amount of reactants and products. Alright, so the equal in equilibrium comes from the fact that the reaction rates are equal, not because the products and the reactants have reached equal amounts. That might be true occasionally, but most of the time either the reaction will be product favored or reactant favored, and we'll talk about what those mean more in just a moment. Now, to give you a physical analogy to what this might be like, so if there's a department store or a mall or something like that, and there's an escalator that connects the first floor and the second floor, people can ride up the escalator and down the escalator. Let's say that there's 120 people on the bottom floor and 40 people on the second floor. And if you sit there and watch the escalator, maybe in each minute 10 people go up and 10 people go down. The amount of people on the top floor and the bottom floor will remain the same as long as the rate of exchange between the two is the same. That's sort of like this chemical reaction where the reactants are forming product at the same rate as the product is forming reactants. Okay, so when equilibrium is reached, the ratio of products to reactants indicates the equilibrium position. And if there are a lot more products than reactants, then we say that the reaction is product favored and that the equilibrium lies to the right. Well, why don't we say to the right? Well, products are found on the right side of an equation. So as this equation is written, the products are on the right and the reactants are on the left. So if reactants are heavily favored, in other words, if there are a lot more reactants than products, then the equilibrium lies on the left. Now, getting into the more mathematical elements of this. So, equilibrium expressions are a numerical or a mathematical way to represent the equilibrium position. So KEQ is the equilibrium constant for a reversible reaction. And the equilibrium expression is saying the equilibrium constant is equal to this combination of concentrations. Now, where do we get all of this stuff from? So this reaction that we've written is just a generic reaction. It has two reactants and two products. Now, if let's say we only had one product, well, you wouldn't need D. So what this is saying is that the equilibrium expression is going to be the concentration of the product raised to the power of the product times the concentration of the other product times the power. By the way, those powers are coming from the coefficients from the balanced chemical reaction. So we'll practice doing this with a real one in a little while. But like, let's say that was at C, the little c was at 2, then that would be squared in the expression. So it's products, and however many products you have, product times product times product, and then divided by the reactants. So reactant A, the concentration of it, to the coefficient of A, and B to the coefficient of B, and so on. If you had more reactants, then you would use more, and if you had less, then you would use just one maybe, or maybe none sometimes. Okay, so recall the brackets mean concentration in molarity, and that's going to apply to things that are aqueous or gases. Pure liquids and solids are not included in the equilibrium expression because their concentrations don't change. A solid, the amount of it might change, but the concentration doesn't change because the solid has a fixed density, and if some of it gets used up, the density of the remaining solid, it's an intensive property density, or and therefore concentration. That doesn't change for solids and liquids. So only aqueous and gases get included in equilibrium expressions. And let's look at some of these meanings here. Now, I'll go back for just a moment. Remember, this is products divided by reactants. So if there's a lot of products, that means we're favored to the right, and that'll be a big number for a KEQ. If you have a big number of products over a small number of reactants, big number divided by a small number gives you a big KEQ. On the reverse side, if you have a lot of reactants and not a lot of products, a small number divided by a large number gives you a small number. So if KEQ is greater than 1, that's an indication that you have a product-favored reaction, that the equilibrium is going to lie on the right. That's just another way of saying products are favored. And if K is a very large number, the product particles are going to greatly outnumber the reactant particles. KQ is a small number, less than 1. Reactants are favored. Equilibrium is going to lie on the left. And if K is a really small number, then the reactant particles are going to greatly outnumber the product particles. Alright, so here's an example. So we got some ammonia, or at least we're trying to produce ammonia. That's what the reaction says. N2 plus 3 H2s makes 2 NH3s. So it tells us that at equilibrium, a 1 liter flask contains 0.15 moles of H2, 0.25 moles of N2, and 0.10 moles of NH3. Alright, and it wants us to calculate the KEQ for this reaction. Now you might be like, well, I don't know how to do that. Okay, fine. So the first thing you got to do before you can do anything else here is you need to write the KEQ, or the equilibrium expression, using the balanced chemical reaction. So let's do that. Alright, so remember, it is products divided by reactants, and the coefficients become the powers. So NH3 is the product, so it goes on the top. Brackets there to indicate concentration of NH3 in molarity, and the 2 from the coefficient. N2, there's not a coefficient, so there's not a power. And then H2, the coefficient is 3, so the power here is 3. Now that we have that, we need to know some values to plug in if we're going to calculate KEQ, so we need to determine the concentrations of each substance. Now they gave us moles, and they told us that those were all in a 1 liter flask. So if we recall that molarity equals moles divided by liters, this will be pretty simple for us. So for example, the molarity of the nitrogen would be the moles of the nitrogen, which is 0.25, divided by the volume of the flask, which is 1 liter. So conveniently, that's just 0.25 molar. Repeat that for hydrogen and ammonia. Remember, they're all in the same container together, so their volume, all 3 volumes are 1 liter. All right, so you've got those. So we have numbers, and then we're going to substitute those into the KEQ expression. So the 0.15 for the hydrogen, the 0.10 for the ammonia, and the 0.25 for the nitrogen. And when you carry out the mathematical operations here, 0.10 squared divided by 0.25 times 0.15 cubed, you get 12. You might notice that this says, it's supposed to be product favored. You're like, well, there's less product. Well, sometimes the reactions, one is not exactly the cutoff number to say there's more products than reactants. But what you can tell from the equilibrium constant is the larger the number that gets, the more products are present. In this particular case, the N2 and the H2, since these are down here, and particularly the H2 is cubed, that contributes to this value being larger. Alright, so let's take a look at another example. Alright, so here's a different reaction. So we got some bromine chloride decomposing. And it says at a given temperature, the equilibrium constant is 11.1 for the reaction above. If the reaction reaches equilibrium and Cl2 equals Br2 equals 4 molar, what is the concentration of BrCl? So let's start off again. You can't do equilibrium constant calculations if you don't have an equilibrium expression. So let's write the equilibrium expression, where that's going to be products divided by reactants. Product, and then the reactant on the bottom, and it's squared because there's a 2 for a coefficient. Right, and then we've got concentration, so we're going to substitute in our chlorine and our bromine concentrations, which we know are both 4 from the information given. And then we just need to do a little bit of algebra. So first off, I'm going to multiply to move the BrCl squared to the other side. And then also I multiplied the 4 times the 4 and got 16. Then I'll divide both sides by 11. 16 divided by 11 is 1.44. And then to solve for BrCl, you need to take the square root of both sides to get 1.20 molar as the concentration of the BrCl. Right, those two examples pretty much are going to cover the extent in honors chemistry of what you would be expected to do with equilibrium constants. Alright, so let's look at solubility product constants for just a moment. So different ionic compounds have different amounts of solubility, and that just means that only a certain amount could be dissolved under certain conditions. So this is an equilibrium situation where you've formed a saturated solution and you can represent mathematically with an equilibrium constant how much of the ions actually dissolve. You have to have some undissolved solid present. So we're going to use the same rules to write the solubility product constant, the KSP. And so for this reaction, or sort of a reaction, the products are the silver ion and the chloride ion, and then they form from silver chloride. So silver chloride is a solid, so it doesn't get included in the solubility equilibrium expression. So only the products, the ions, the silver and the chloride, get included. And let's say that there were 2 chlorides, then this would be like Cl brackets squared, just like regular equilibrium expressions. And you could solve all kinds of things for these. But for honors chemistry, I'm showing you, but we're probably not going to do a whole lot of calculations or anything with these. Alright, so thanks for watching, and I'll catch you in the next video.